Hey, Sophia, did you get my email?
I have not checked again.
Okay. I'll set up a Dropbox folder that you can just submit things to, and that should take care of it. Clearly, I'm not getting it done before class starts because I just saw your email.
Uploaded it to like YouTube, so I can send you the link, or I can do the Dropbox.
Oh, you can also just send me a link to your YouTube video. That works also.
It's still loading, but I can do that when it's done.
Okay, cool. That's fine. As long as I can see it, it doesn't really matter to me where it's at. If it's on Moodle, that's convenient for me. If it's on YouTube, that's also convenient. If you sent me a link via Loom, that also works. So. Dr. Judd, you are now host.
Excellent, thank you.
Sure, no problem. Grant, where are you at?
I'm in the PLC right now.
Oh, I don't recall that ceiling in the PLC. It's like a wood slat ceiling. Oh, I guess I've never really looked up. Huh. Learn something new every day.
Smith. Okay. Still hearing some chimes, but it's 12:30, so we'll get started in just a second here.
Dr. Judd, can I do a couple of announcements here at the beginning?
Yep.
Monday, your literature summary is due. I am still working through the last of the methods and results sections. I think I have 5 or 6 more to go. I'll send them out later on this afternoon, hopefully. But before that, there are some general things that you should be paying attention to. Make sure that you format it correctly. There are formatting instructions in the guidelines to the literature summary, so follow those. It's about font sizes and margins and whether or not you put your name in the body or whether you put it in the header, et cetera, et cetera. The reason we have these is that there's a 2-page limit. And if everybody follows the same fonts, the same spacing, the same margins, et cetera, everybody has roughly the same number of words to get across the idea. And the idea is that this is a summary and then some critical thought. And you only have a certain amount of space in which to accomplish that. The reason for the space limitation is we want you to be concentrating on the things that are actually important rather than getting overly embedded in the details, which sometimes people have a tendency to do. So it should be about 1.5 pages of summary and about 1/2 page of critical thought, thinking forward to what you would do next if you were going to continue working in this particular system. While you do that, a really good way to fit it all in there is to order your thoughts before you sit down and start writing. So in the methods and results, I was noticing that some people were jumping around from topic to topic quite a bit. Try and put it in a logical order. That logical order will also help you with keeping concise. Make sure that the terms that you're using are terms that you really are familiar and comfortable with the meaning of those terms so that you're using those terms accurately. Be concise. One of the terms that you guys are using inaccurately sometimes is the term adapt or adaptation. There's a physiological meaning of the term adaptation, and there's an evolutionary meaning of the term adaptation. And from the context, it looks like some of you are using an physiological meaning of the word adaptation. There is adaptation that organisms go through. You know, for example, seasonal acclimation is a type of physiological adaptation that comes and goes as the environment changes. But evolutionary adaptation only is something that happens over multiple generations of time. So you can't talk about a bird at the Galapagos Islands adapting. That bird has all of the characteristics and traits that it's ever going to have. It's set in time genetically. It's not changing its allele frequencies. So I think those are the big things that jumped out to me as I've been going through your methods and results section. Dr. Judd, do you have anything to add?
Yeah, 2 things. When you're writing about this stuff, you're going to be talking a lot about bimodal distributions, right? Make sure it's clear that you're talking about a bimodal distribution in something like beak size, if that's what you're talking about, and not in finches or just a bimodality without specifying what you're talking about. It's a distribution of something. It's a pattern we see. So you got to tell what the pattern is about. And then I also, if you get this done, if it's mostly done now or you get it mostly done tomorrow, find a classmate, find a partner, trade, and peer review your own work. Ask your classmate, is this clear? Can you follow? Do you think that I matched what the paper was about? And do the same for your partner, and then you guys can revise each other's work. Professional scientists do this constantly, so it's something you can jump into right now when it comes to working together.
On Moodle, there is up at the very top of the Moodle page in the general information where there's also a lot of stuff about the literature summary. I put a link to a very brief Inc. magazine article where they were interviewing Judge Ruth Bader Ginsburg's clerks about how she influenced their writing styles. And you will see some really good advice in there. There are 4 points. It says there are 3 points, but there are really 4 points. It's a very quick read. I think you'll gain something from looking at that, to look at a Supreme Court justice's approach to writing, because for one thing, she is a Supreme Court justice, was a Supreme Court justice, and 2, you will see many of the same things in her advice that we've been advising you about. So we're not just making this stuff up. There are other people who think these things also.
Any questions about the Henry?
Yeah, I think that's all I want to say about it. So.
Okay. So before we dive back into those phase plane diagrams that we ended on this time, I want to take a moment and back up and make sure you guys remember the foundational stuff that we've been using these last 2 lectures and when we were doing the exponential growth models a while back. So to that end, I have created another Kahoot quiz. So you should see a purple screen with a pin. So if you go to kahoot.it and you enter in that pin, you should show up as a player, and we can go through these, I think 4 or 5 little questions I have just to get your juices flowing. And you can do this on an iPad, a phone, or on a computer. Let me check participant list. Share. Oh, here it is. 29 participants. Got it. 1. Okay, we'll let a few more people find their way on. Excellent. All right. So before I hit the start button, 2 things. When you see these equations, it's not important that you try to memorize the equations right now. It's important that you memorize what the parameters and the variables mean, and you can explain those parameters and variables in plain English one at a time. Then you can piece things together and recognize equations when they're presented to you, and eventually you'll memorize them. But right now, we just want you to memorize what the variables and parameters are, what they mean, and how you can explain those in plain English. That's a study tip when you're going over this stuff. It gives you the capability of using the equations. So let's start the quiz. Ready for the Kahoot? Start, please. Here we go. Competition. What is dn by dt? Excellent. Okay. Can someone out there tell me what parameter we use for the instantaneous rate of increase? Actually, I think, well, let's do it anyway.
It's a little r.
It's little r. Good. All right. So I just helped you guys. That's a common one to be confused about, which is why I put it on the Kahoot quiz. So make sure you know the difference between those 2 when you're studying. Yeah, I forgot that this was my other question. So what is r? Little r. Excellent. Good. So the population growth rate is going to be individuals per unit time, like per year. Individuals per year, that's the units. The per capita rate of increase, or the instantaneous rate of increase, let's say per capita, is individuals per year per individual. So it's individuals over individuals times years, or whatever your time unit is. All right, next one. In those Lotka-Volterra competition models, what was that alpha value? This is a tough one. Yeah, maybe I should have put a little more time on this one. So the reason this was challenging is because you have to really watch for whether the question says interspecific or intraspecific. So it's the effect of species 2 on species 1. We'll see that again in a little bit when we work together as a class. And it's also, it should be made clear in the screencast that I posted. what's on the axes of those Lotka-Volterra phase plane diagrams? All right. So in the logistic growth model, you look at how a population changes through time in just one species. And that would be the blue answer. In the phase plane diagrams, the coordinates in the graph, the x, y coordinates for any point are the size of one population on the x-axis and the size of the other population on the y-axis. So hopefully this little quiz has shown you what things you need to make sure you get when you are either going over your notes or watching the screencast. And I think this is the last one. This is the last thing we talked about, and this thing we're going to talk about first. What conditions are necessary for stable coexistence of two species? And I left extra time for this one, the way I should have for the other one. Good, excellent. That was good to see. When interspecific competition is weak and doesn't limit a population as much as a population limits itself in intraspecific competition, when that's the case, you can get stable coexistence. Notice that in green, I said that inter is really strong relative to intra. In the yellow, I put a typo. I just wrote intra twice. And in blue, I made alpha and beta great. What did I do on that one relative to intra? Oh, I put strong again. So it's just a, yeah, in green, I put the greater than, and blue, I put the less than. So you just gotta be careful with.
Nathan, can I add something?
Please.
Yeah, so when you think about alpha and beta, you're multiplying those times the other species density. And so if it's at 1, you're basically saying that the other species is equivalent to the first species. So if you have, alpha in 2, you're basically saying that species 2 is equivalent to species 1 in terms of how they're using resources. And so that greater than and less than 1 is pretty important. That 1 kind of marks a boundary line between where you would go from stable coexistence to something else.
Good. Okay, let's see what the totals are. Nice job, Grant. Nice job, Sydney. And look at that. This is a testament to coming into office hours, everybody. All right, doing a good job. Now I'm going to stop this share and switch over to a whiteboard here. Okay, so we drew a phase plane diagram at the end of class last time, and it looked like this. The x-axis was species 1, which has some population size measured by the variable n. The variable n takes the value of the population size of species 1. And on the other axis is the population size of species 2. So any point on this plane is just the condition where species 1 is at some population size greater than 0, and species 2 is at some population size greater than 0. Now, remember that along this axis, you're kind of, it's almost like you're looking down at a logistic growth curve like this, right? There's going to be some carrying capacity, there's some 0 population size. Same thing's happening here. 0 population size, some k value, and then all possible values greater than k. Same thing is happening on the other axis. Starting at 0, there's going to be some k value somewhere on that axis. So lots and few, and lots of individuals. So let's look at some of the parameters of the phase plane diagram that we looked at the end of class last time. If interspecific competition is weaker than intraspecific competition, then you'll have this scenario where a species effect on itself, so species 1 affecting itself, is less than, sorry. Let me just move this down. A species' ability to affect itself is greater than the effect of competition from some other species, from species 2, then what's this value going to be? Basically, what kind of a number are you going to get here if A sub 1, 2 is smaller than A sub 1, 1? If interspecific competition is weak.
Number smaller than 1.
Good. So let's just say we get 0.5, and that number is what we call alpha. Similarly, if we do the same thing for the second species, effect of species 1 on species 2, divided by the effect of species 2 on itself, let's set this one also to, yeah, let's just do 0.5 for this case. And that, what parameter do we call that one? What letter do we use for this one?
Beta.
That's correct. We use beta. Yeah. So in this example, let's make the effect of intraspecific competition equal for both species. So A11 is 0.01 or 1 over 100, and A22 is also the same value. So they both have the same carrying capacity. So we just find this, we plot K1 here equals 100. And then we need to make this 0 net growth isocline. We need to draw this line on the plot. So we had to solve for the value of N2 when N1 approaches 0 or gets all the way to 0. Does anyone remember how we took the equation dn by dt equals Rn over, we did, well, the way I do it usually is 1 minus N1 plus alpha N2 over K1. Does anyone remember how we solved for N2 in this scenario when we first set dn dt to 0 and then we set N1 to 0?
Did we get like K1 over alpha?
We did. So if you don't remember how we did that, that's why we have these things recorded and you have your notes. So make sure you understand how we got K1 over alpha for this. But the point is that if we take our N1 all the way down to 0, and then we go up this N2 axis, K1 over alpha, if K1 is 100 and alpha is 0.5, what's our N2 value going to be?
50.
It's going to be divided by 0.5.
Oh, so 200.
Good. So K1 over alpha is going to be 200. And it turns out that is exactly the same as 1 over the effect of species 1 and species 2. So it all circles together. 1 over A12 is 200, and K1 over alpha is also 200. So now we can connect these two lines, connect these 2 points with a line, and we call this a zigzag for species 1. Who remembers what that zigzag stands for? It's an acronym. It stands for zero net growth. Zero net growth, so that's a Z. And it's an isocline. So the straight line means isocline means same. So it's a stable sort of line such that for any population size of N2, if N1 falls on that line, the growth rate of the population is 0. So if there's no species 2, then you're at carrying capacity for species 1. But if species 2 is present, that carrying capacity for species 1 is depressed because species 2 is taking up some of those resources. Okay, so we can do the same thing for the other species. It's exactly the same process. dn by dt equals R2, N2, 1 minus the effect of species 1, right? Because interspecific competition over that. So I already told you that K2 is also going to be 100. K2, 100. How can we solve for the value of N1 when species 2 declines to 0 and the population growth rate is also 0? You could do the algebra, or you could look at how we did it for species 1 and take an educated guess on what that equation is going to be.
Is it going to just be divided by 0.5 again?
Yeah. And how would you say that in terms of the variables themselves?
So K2 over beta.
Exactly right. Good. So that's going to get you 200 because it's still 100 divided by 0.5. K2 over beta. Now we can connect these two. Now our phase plane is divided into 4 regions. 1, 2, 3, 4. And you can look at how population size changes with each of these. So for this lower quadrant, where population size of both species is low, below both natural carrying capacities, are you to the left or to the right of the black isocline?
Left.
So which way is the population going to change? Which direction is it going to change? If you're below carrying capacity.
It would increase.
Yeah, it's going to increase towards the isocline. And I want you to think about this as though you're stuck on that axis and you can only move right and left. What about up here? Are you to the right or to the left of the isocline?
To the right.
Now, notice I'm at carrying capacity, but there's also 120 individuals of N2 present that are depressing that carrying capacity. So how's the population size going to change?
Decrease.
Decrease towards that isocline. What about in this spot up here in the upper left? Population can increase or decrease.
Increase.
And lastly, down here, someone else in the lower right. You're at some value of N1. Is your population size going to increase or decrease from that starting point?
Decrease.
Going to decrease. Good. Now, pause, switch gears. We're switching to blue. We're going to look at how the population size of species 2 would change. Say we start down here where population size is very small. What direction should I draw that arrow?
Up.
It should draw it up, right? Dominic, can you tell me why it should go up? Why the arrow is pointing up in plain English?
Because the population will increase.
Yeah, it'll increase towards that zero net growth isocline. What about up here in the upper left, upper left, straight above that? How do you get to that? How do you get back to the isocline? Right? I see people nodding and stuff. So what about up here? How do you get back to the isocline? What direction do you draw the arrow?
Down.
Down. And finally down here.
Up.
Yeah. Okay. Now I want you guys to get in the habit of thinking about this one axis at a time. But once you've drawn all these pairs of arrows, then you can start to combine the vectors. So can someone tell me, once again, in simple words instead of equations, what is happening to the population size of species 1 and the population size of species 2 at this point on the graph?
There is just as many births as there's deaths. It's equalizing.
Yeah, exactly. So for both populations, birth rate and death rate is balanced, and the carrying capacity for each one is depressed by the presence of the other, such that they have a stable population size that is below each of their respective carrying capacities, right? And the reason that they're below is because the other species is making up that difference in terms of resource use, I mean. So this is the case that we call special, this is the special case that we call stable coexistence. And it happens when interspecific competition is weak relative to intraspecific competition for both species in your scenario. All right, now let's stretch with your new muscles here, right? Let's say we've got a species 1 and a species 2. And we still are going to have alpha and beta are going to be equal to 0.5 for both cases. So the strength of interspecific competition or intraspecific competition relative to inter, right, that ratio is the same as it was before. But this time, I'm going to make K1 is going to be equal to 200 individuals, and K2 is going to be equal to 600 individuals. Which species, species 1 or species 2, has stronger intraspecific or within population competition?
K1.
Good. Why?
It's got a smaller number, but it's got the I don't know. You got a smaller number, so there's more competing for the same, or there's less competing for the same thing, I guess.
That's good. And you could do the same thing this way, right? So for species 1 and species 2, which number is bigger, 1/200 or 1/600?
1/200.
Yeah. So that intraspecific competition is a larger number, so it's stronger if you use it in this notation of A11 versus A22. So well done. So let's draw the isocline for species 1. Where do we, if I put, let's see, if I put 200, sorry, I was using the eraser. If I put 200 individuals right here for that K1, where's the other side of that isocline going to be?
At 400.
Good, 400, because it's K1 over alpha. Then we draw that isocline. Now we'll switch colors. Now K2 starts up here. Where's the other end of that isocline going to be?
$1,200.
Good. Yeah, it's going to be way out here. K2 over beta equals 1200. So how many regions are there in this phase plane?
3.
Good. Yeah, that's great. Yeah, there's 3 instead of 4 because the lines don't cross. So let's think about species 1 in black. You're down here. Which direction is the arrow point?
I feel like I'm the only one answering here. Come on, guys.
Thanks, Connor. Yeah, someone else. Which direction would that
To the
arrow?
right.
To the right. Thanks, Tom. What about out here if you're above carrying capacity?
Then it's to the left.
And if you're out here way above carrying capacity, it's still going to be to the left, right?
Yeah.
You say correct, not right. It's like we're driving. Okay, now we'll switch to blue. We're down here again. How do you get to that isocline? Somebody else. We got Dom and Connor talking a bunch.
The arrow would be upwards.
Good. And up here, in the middle one,
Up.
and way out here,
Down.
down. So then if we sum these vectors, you can imagine that if you start way out here and your population sizes of both species starts to decline, eventually you're going to approach the blue line. Remember, as you approach the blue line, your rate of change is going to decrease. So that means that we're going to end up in this kind of a scenario. Here, the rate of change going along the x-axis starts to slow down quicker than the rate of change on the blue. So you'll cross over that isocline. And once you cross over, notice that the sort of net effect along the x-axis is going to be negative again. So you'll end up with a phase plane that takes you to this consequence, where you have 0 individuals of N1 and N2 is at carrying capacity. So this is realistic in the sense that you could imagine a place where there are 2 species that compete relatively weakly with each other, but significantly so. That's why the values are 0.5. But in this environment, species 1 tends to struggle a bit, so there's more competition within the species, and species 2 does really well. So it would make sense that species 2 would outcompete species 1 in some places, even if they have some shared food resources. This is what we see all the time. If you put 2 species together, one's a stronger competitor, it'll outcompete and displace this first species, at least in that local area. If we do the same thing, but it's reversed, such that species 2 has stronger interest-specific competition, then you'll get this kind of a scenario where K1 is 500 And K1 over alpha is going to put you way here to 1,000. And 2 might have a stronger intraspecific competition. So you end up starting maybe at a carrying capacity of 100, right? And 100 divided by 0.5 gets you out here at 200. So that's K2 over beta again. Now you've got the same situation where you've got three regions to the phase plane. And if you're here, you go down. Here you go up. If you're here, you go up. Oh, sorry. I switched my numbers here, but the point is blue. Oh, I just drew the same one twice, didn't I? I do the same one twice for you guys because I was going too quickly. This is why I keep saying when we talked earlier that it's important to go slow. Yeah, 500, 1,000, 100, 200. Yeah, let's do it this way. I'll be quick. Three here is 100. There we go. $500 divided by 0.5 gets you way out here at 1,000. Okay, now we're back on track, guys. Sorry about that. But hopefully you're able to intuit where we're going with this. That'll go to the right. That'll go to the left. This will still go to the left. Then we can do the blues. Now when you combine them, yeah, you're below and you're below. Paul, is it obvious what I'm doing wrong here? Now that I'm in front of everybody instead of on my notes?
Doesn't appear that you're doing anything wrong here. Do the resultant vector between the two lines.
Okay. So now you end up, once you cross this isocline for species 1, and you should start declining again and ending up going toward, oh, I see. I just had my colors were confusing me.
Yeah, and I generally try and draw that resultant vector all the way to the endpoint.
Yeah.
Yep.
Okay. So in this case, you end up with species 2 winning, which is actually what I said before. You can
actually, that
switch
second resultant vector, at some point, it has to cross the zero net growth isocline of species 2.
Yeah, it has to.
Yeah, there you go.
These. Because initially there's so many members of individual 1 that it's going to take you below that the blue isocline. That's why Paul pointed that out. When
And if
when
you-
population of one is still really large, you will get below that blue isocline.
And if you simulate this in the Populous program that Dr. Judd introduced you to, you'll see the trajectory go. You can show it in isocline space. You'll see the trajectory go until it crosses that line. And as soon as it crosses that line, it starts bending towards the endpoint, wherever the equilibrium endpoint is.
So if you try drawing these or you go into Populous, notice once again, I've made K1 have stronger intraspecific competition. The reason I confused myself for a moment there while you guys were watching is because I wanted a situation where K2 equals 100 and K1 equals 500, but I kept the alpha and beta the same. So I could ask you a question: how would this phase plane look under this scenario? Not the one I just drew, where we switch who has stronger versus weaker intraspecific competition. Okay, our last one that we're going to think about, that I hope, let's see, make sure I have my notes, make sure it looks good. Okay. There's one other situation that theoretically could arise. We could have a situation where K1 equals 200 and K2, maybe it's got a little bit stronger intraspecific competition, but not super stronger. So we'll go 150. So let's do, stick with the black for N1. We'll find that K1 value of 200. We'll stick with blue for K2. And we'll go for that 150. Now we're going to set it so that A12 over A11 is greater than 1. Who can tell me what this means in plain English? If A12 is greater than A11. Using the terms inter and intraspecific competition. Someone new. If you recall, A12 is the coefficient of interspecific competition, the effect of species 2 on species 1. And A11 is the effect of species 1 on itself. So what has to be true about the relative strengths of inter and intraspecific competition for this ratio to be greater than 1?
Interspecific competition is higher.
Yeah, that's correct. Good. So if we had an alpha value that was 1.5, greater than 1, right? And similarly had a beta value that was also 1.5, then what would the K1 over alpha value be?
$300.
Yeah, it'd be 300. And what would the K2 over beta value be?
$225.
Sorry. Just double checking here. So this is the same thing we struggled with before. If you take 200 and you divide it by 1.5, what do you get?
133-ish.
Yeah, do you guys see that? So this line that connects 200 to this K1 over alpha should actually be down here at about 133. Similarly, if we switch back over to blue, we take this K2 value, 150, and we divide it by the beta 1.5. What value do we get?
100.
Yeah, good. Now, how many regions are there in this phase plane diagram?
4.
There's 4 again, but we have a new situation with these 4. So in order to understand that, let's think about what happens in this lower quadrant. What's going to happen to the population size of species 1 and species 2? Which way do you have to go to get to the isoclines?
Up.
Up for 1, and what about the other one?
Right?
No. And out here, it's just the opposite, right? But what about in this region? Which way do you go to get to the isocline in black?
Up and to the left.
To get to up and to the left is, look carefully. Which way do we draw the line to get to the black? Which way do we draw the arrow to get to the black line?
To the right.
Right, good. And which way do we draw the arrow to get to the blue line? Imagine the blue line crosses and goes into that negative region.
Down.
Down, good. And up here in this region, which way do we go to get to the blue?
Up.
Up. And to get to the black, out that way, right? So then if you draw your resulting vectors, you still have this interesting crossways, this interesting intersection here, where if you had exactly this many individuals of species 1 and exactly this many individuals of species 2, everything's going to be stable. But not everyone is born at the exact same time every day, or not everyone dies at the exact same time every night. So there's always going to be situations where you might deviate just ever so slightly, even if the net change is 0. So if you ever fall off of this equilibrium point, you could end up in this lower right quadrant or this upper left quadrant. And in that case, the other species will win. So this is an unstable equilibrium in the center. It's still an equilibrium because it satisfies that equation where you get dn by dt equals 0 for both populations. But it's unstable because if you deviate one way or the other, then you'll either species 1 will outcompete species 2, or species 2 will outcompete species 1. Now, I want you to think for a moment, away from the math, away from the numbers. This is kind of not what we would expect to see in the real world, given what you know about species coexisting. It doesn't make a whole lot of sense that intra-specific competition, that a different species would affect the growth of a species of interest stronger than it affects itself. Say you've got squirrels and groundhogs, and they're eating similar, or squirrels and chipmunks. They're eating some of the same foods, but maybe the chipmunks are spending more time getting grubs and roots because they burrow sometimes, and the squirrels aren't. So a squirrel is not going to be better at getting chipmunk resources than a chipmunk is. The chipmunks are going to compete with each other more strongly than they do with the squirrels. And the chipmunks don't spend as much time in the trees eating all the nuts out on the tiny branches as a squirrel does. So a chipmunk's not going to be better at being a squirrel than a squirrel is. So this situation where inter is greater than intra is unusual. And it's more typical that intra is stronger, so that your alpha and beta values are less than 1. And so you end up in a world where many species that have similar resource needs actually do coexist just fine, because inter-specific is greater than intra-specific competition. Make sense? So this one is the unusual situation. Okay, that went a little longer than I expected, but I hope it was useful. And I encourage you guys to play around on Populous instead of watching me scribble on a whiteboard. I think that'll be really useful for you. So give yourself 45 minutes or something to really see what happens when you play around on Populous. Participants. Any questions? All right, then we're going to use the rest of the time, I guess, to talk about adaptive radiations. And Paul, I'll let you decide how you want to use what scraps I've left you.
Yeah, I'm gonna change things up a little bit. So what I was originally gonna have you do is to break into your groups and present your presentations to one another. But we really don't have time to do that because we only have about 12 minutes left in class, and it would probably take about 20 to 25 minutes to do effectively. So what I want you to do is get together outside of class with one another on a Zoom meeting or something like that. Have you guys been setting up Zoom meetings with one another for classes?
In general?
In general?
See some nods.
You guys got to talk to me.
My group has done it a couple times.
Okay, so figure out how to do that. Get together with your group that you've been put with in breakout groups in the past. You know who those people are. And present those to one another over the weekend. So what I'll do is I'll just start running through what I would have said after you had done that in class. And this might actually help inform your presentations that you make to one another. When you're done seeing those things as a group, come together and say, okay, as we see one another present to one another, what are some things that we learned about what makes a good presentation and what makes a not so good presentation as we go through this? I also recognize that the first question in that list of things that you're supposed to address in your presentation is what an adaptive radiation is, so kind of providing a definition. Once you feel like you've gone through enough of those with your group members that you kind of are arriving at what a good definition of an adaptive radiation is, you can forego that first slide in your presentation if you want. So homework for Monday is view your presentations with one another, and then rather than concentrate on, well, what was the actual content of the information that the person gave me, because everybody's doing different adaptive radiations, those will be different from group to group. Use that information to help you understand what an adaptive radiation is and how they operate, but then concentrate also on, well, what did this person do that made that presentation useful and informative? What could they have done that would have made it more useful and more informative? What kinds of things are you seeing people doing that really distract from being useful and informative? And I say that right before I give you a presentation that might or might not be useful and informative. So I'm going to share my screen with you. Can you guys see the PowerPoint?
Yes.
Okay, cool. All right. So unfortunately, in order to talk about adaptive radiation, we have to back up a little bit, and we have to talk about the process of speciation. And so that's what I want to begin with. So we're going to introduce you to species definitions. How is it that we go about defining what a species is, the mechanisms by which species form, mechanisms of speciation is what that basically is, and then explain what adaptive radiation is and how the process of an adaptive radiation happening proceeds. So when we think about species, oftentimes we just look at a species. These are some plethodonid salamanders from the eastern United States. And when we see some other salamanders, these are also plethodonid salamanders. They're in the family Plethodonidae. When we see some other plethodonid salamanders that look different, we would say that these two things are different from one another. And that decision is made basically on the basis of morphology. If two things look different enough, and you can argue over what different enough means, then those two species are different species. And so there is a morphological species concept that uses a morphological similarity as the distinguishing criterion. But oftentimes the example that you see in basic biology textbooks, the definition that you see in basic biology textbooks is the biological species concept, which was put forth by Ernst Mayr in 1942. And this is it directly quoted from him: groups of actually or potentially interbreeding populations which are reproductively isolated from other such groups. And so you're members of the same species if you can interbreed, and you're not members of the same species if you're incapable of interbreeding. And that also has a certain sort of internal logic to it, although there are all sorts of problems with this biological species concept, which we're going to see in just a minute. So here we have two dinosaurs. How can you tell that they're different species if you're using the biological species concept?
You can't.
Anybody?
You can't really.
Oh, Connor, not you again. Somebody else other than Connor. No, you're fine. I'm glad that you're into it, but I'm going to put you on mute for the rest of the day. Somebody else. Cody. Why does the biological species concept not work for this?
Well, isn't it because it's like a fossil and it's older? Maybe?
Oh yeah, it's a fossil. You can't test these things to see if they interbreed. So yeah, that's exactly it. So these things, you would just have to rely on nothing more than morphology. And also the only morphology you have is bones in this case. Dr. Judd works with fossil plants. He has the same problem. All he has to go on are the evidence that is in fossils. He's never going to take these species and interbreed them. You're not doing that, are you, Dr. Judd?
No, we are not.
Okay,
But we
I
do
didn't,
have more than just bones. We have all the anatomy.
Yeah, you have all the anatomy, even cells, amazingly enough. So, so this is a situation where the morphological species concept would be more useful to you. But then we have these two species where these things look virtually alike. But when you listen to them call, this one sounds like this. Can you guys hear that?
No.
Can you hear it? No, you cannot hear it. Okay, hold on. Stop. New share. Okay. Can you still see the PowerPoint?
Yes.
Still see it? Okay, now can you hear it? No. Okay, all right. In the PowerPoint that is online, click on these buttons and you'll see that this is a very fast trill and this one has a very slow trill. And I'm listening to it. It sounds so pleasant.
You sound first.
What's that?
You do your best representation of it for us.
Oh, I can try. Let's see. Let me listen to it. Come on now. And this one goes. Warble, 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 warble. Warble, 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 warble. It's much slower, way slower. And now I've totally embarrassed myself, and this is going to be on the internet, and I'm going to die. All right. So in that case, these two species are species that formed due to a genome duplication. This one has, if I'm recalling correctly, this one is tetraploid and this one is diploid. And they differ only in the size of the genome. And so there was a mistake in meiosis at some time in the past. And this basically is a tetraploid and a diploid version of the same frog. But because they have different ploidy, they're no longer reproductively compatible, even though they look exactly alike. The only way you can tell them apart is by listening to their call or by looking at their cells under a microscope. And the blood cells are different sizes because in amphibians and reptiles, the nucleus of the cell is still in the blood cell, unlike our blood cells. And so the nucleus is bigger because there's more genetic material in the tetraploid version, and the cells are actually visibly bigger. So the morphological species concept wouldn't work here. And so we could invoke the evolutionary species concept, which is put forth by this guy, KU, named Ed Wiley, a lineage of ancestor-descendant populations which maintains its identity from other such lineages and which has its own evolutionary tendencies and historical fate. Well, this would cover this situation because these are now different lineages because they're now separated genetically from one another, and they are going off kind of on their own evolutionary trajectories.
Hey, Paul,
But yeah, what?
I think that the screen share got changed, so we're still on the frog slide.
Oh gosh, darn it. I was trying to get sound and now I'm just messed up. What is it at now?
Perfect. Evolutionary
Okay.
species.
Okay. Well, now maybe I can. Can you hear this now?
Yeah.
You can? No?
Oh, no.
No.
I thought
Okay.
you said.
All right. All right. So an evolutionary species concept would apply now to these frogs because these frogs are kind of on their own evolutionary trajectory. But the evolutionary species concept is not a panacea either, because we have things like Spitacilus gularis, which is a whiptail lizard that occurs in the desert Southwest. And then we have Spitacilus inornata, which is another species that shares the same space. They're sympatric with one another. Well, at some time in the past, these two got together and they created offspring. And now there's this new species, Spitacilus uniparens, which is hybrid offspring of these two parental species. This is an all-female species, and they reproduce through parthenogenesis. And as a result, they don't breed with anybody to produce new offspring. And so parthenogenic species are problematic for the evolutionary species concept because in this case, every individual is its own lineage because they don't ever interbreed with other individuals. And so it would be ridiculous to call each individual lizard out in the desert of the desert Southwest in the United States its own species simply because they all have their own independent lineages because they don't interbreed with anybody because they are parthenogenic. They create new offspring from unfertilized eggs. So what I'm going to do is I'm going to put the rest of this in a screencast. Also go through that because we talk about modes of speciation over here later on, and then we talk about at the very end we talk about what an adaptive radiation is, and how they operate, and you need all that information as we think about the adaptive radiation, which is the Galapagos finches, which is kind of the point of Monday, actually. So look for a screencast posted later on today. I'll send out an email to all of you when it's up on the YouTube site. Any questions? Alrighty, I will see you guys on Monday.
Dr. Kowinski, can you
Yes,
hear
ma'am.
me?
I can.
Oh.
I was just about to leave, but I'm here now.
Okay. Will you be on campus after the next period, after 2:55? Either you or Nathan, Judd.
I can be, sure.
Okay,
I'm gonna go in. I'm gonna go into the field and look for insects for one of the groups, but I can be back up here then.
Okay, because our group messed up all the samples and we need to collect them again this weekend. I just found out.
How'd you mess them up?
So we collected the plants that were not mature enough to collect the seed. And also we measured the distance from the edge wrong, like totally wrong.
Okay, what group are you in? What's your question?
The history group.
Oh, the life history group. Okay, all right. So you need mature. Well, the nice thing is all of the plants virtually are ready to be harvested now, so you don't have to worry about that part. Any plant you collect at this point is going to be harvestable.
Oh,
Did you
But-
go through this with Dr. Judd? Did Dr. Judd look at your plants?
no, I haven't been to the lab and I'm planning to go to dry them this weekend, but I don't know if I can.
Paul, if you stop by after that class, I have class next too. If you stop by after that, I'll show you a couple things and we can call. I was going to tell them to call campus safety if they need access to the room. Is there anything else that we should tell them?
Sure, and I'll put a note inside the room
Okay.
with
All right,
everybody's
thank
name
you.
on it.
Yeah,
Okay,
I
so,
have to
so
go.
I guess go see Dr. Judd, it sounds like.
Okay, thank you.
All right. Sure. Thanks, Nathan.
Yeah. Dom, let me see which email that was. I want to make sure I got.
We can't hear you, Dominic.
Oh, I
You
see.
need to unmute.
It was the most recent one because Moodle
Okay.
wasn't cooperating, so I attached some work to the file and sent it to you
Oh,
at the beginning of class.
Okay, I've got this. I've got the file, so I'll make note of that. And
Okay, I
we
appreciate
will,
it.
yeah.
Is there
okay.
another way I could turn it in besides that, or because it still wasn't
if it-
working on my iPad?
You can. It's not allowing you to upload a JPEG, right? That's the point.
Right. Yeah. Usually Pages
JPEG's not a
doesn't work,
video
so I
file.
transfer the file over to. What'd you say?
JPEG's not a video file.
Gotcha. Okay.
Oh yeah, because my Loom, is that what it's called? The new application. It wasn't working for me, so I was uploading the image of my outline as Dr. Judd showed to me in an email before class.
Okay.
Right about before class, I said if you've done the work besides the Loom, at least demonstrate somehow.
Oh yeah. Dr.
I
Judd
have
has
it
to
on.
go to class. If you're having trouble, what kind of computer do you have, Dominic?
I don't have a computer. I just the iPad.
Oh, you don't have a computer. Okay. All right. So how are you saving your work and all that? Whose computer are you on
I
now?
usually do my work. What'd you say?
Whose computer are you on now?
I'm using my iPad for the Zoom class, and usually I take
you
notes
got your
by
iPad.
hand. And,
Okay.
yeah.
Come by the office and I'll give you a hand.
Okay. Appreciate you.
Sure, no problem.
You're being good.
Thank you. You have a good day.